Perfect. Hello, everyone, and welcome to another meeting of our reading group. Today, we have another great speaker. We have Karen Livescu from TTIC. And as always, if you have any questions, you could write it in the chat or you could raise your hand and ask the question directly to the speaker. Without any further ado, the stage is all yours.
Thank you. I see there's already something in the chat. Oh, okay. That was you. Um, yeah, if you notice that there are questions and I'm not answering, please feel free to alert me to it. I might miss them in the chat. Um, but I'm very happy to take questions as we go along and make it interactive. I think this is a little bit of an maybe unusual topic for this reading group. Um, my research group works on all modalities of language, spoken, written, and signed. So today I'll be talking about sign language understanding in the real world. And just to just to get oriented, I'm going to start with a little bit of background. So, like I said, there are multiple modalities of language, written, spoken, and signed. Um, as we probably all know, there are roughly 7,000 spoken languages in the world. Of them, maybe about half have a standard written form. There are also a couple hundred signed languages, and these do not have any standard written form. So these are always unwritten languages. And so this is what we'll be focusing on today. So I'm going to give a little bit more background about sign language. Here's an example video, conversation between two American Sign Language users, along with an English translation underneath. It's just going to loop. Um, and so sign language is a type of language in which meaning is expressed through gestures of the hands, upper body, and face. It's used by upwards of 70 million deaf people worldwide. Um, for American Sign Language, which is the main sign language used in the US, there are over 1 million users of that. Sign languages are independent of spoken languages. They have their own lexicon, syntax, morphology, phonology, which is not related to the local spoken or written languages. So, for example, American Sign Language, British Sign Language, and Australian Sign Language are not mutually intelligible. And like I said before, no standard written form. For the purpose of research on sign language processing, there are some technical challenges that include these being low resource languages. So they share all of the challenges that low resource spoken and written languages have. They're unwritten in addition to that. Um, th- Other technical challenges are similar to the challenges that we have in spoken language in terms of speaker variation and pronunciation differences. In sign language, that translates into intersigner variation, co-articulation between signs, quick motions. And then a final technical challenge that's specific to sign language is that video is computationally demanding, just a lot more demanding than text or audio. Um, One special component of sign language is finger spelling. Most gestures in sign languages correspond to a single sign, which is roughly speaking more or less a word. But for words that are um, outside of the standard lexicon of that sign language's signs, like names or technical terms or organizations, people will instead use finger spelling. So, finger spelling is the letter by letter signing of a word in a spoken language. So, the example here is the word pirate, which is finger spelled with hand shapes for pirate. And so in any sign language, there'll be one hand shape or trajectory corresponding to each letter. And the diagram here shows the finger spelling alphabet for American Sign Language. And depending on the domain or the context, there might be up to 12 to 35% of uh, lexical units in American Sign Language that are fingerspelled, and the rest will be lexical signs from the sign vocabulary of the language. So for open domain sign language understanding, fingerspelling can happen a lot, and so this is crucial to deal with. And in my own research group and in my group of collaborators on sign language, we started with fingerspelling. Um, so I'll be talking a little bit about that later. Now, research in sign language is spread across a bunch of communities, so it can be hard to locate the home of sign language research. What I'm showing here is a graph of number of papers over time in Semantic Scholar that mention sign language in their abstracts. And then the yellow bars are the ones that correspond to just computer science and engineering conference and journal publications. So these have had a steep rise over the years. I'm sorry, my arrow here is on the wrong year, but I meant to point to 2024, where there were 1553 papers in computer science and engineering conferences and journals on sign language. And how are they distributed? It's a little bit hard to tell because all of these different anthologies have different search interfaces, but I tried. I believe in the ACL anthology, there are about 1,200 papers on sign language. In the ISCA Speech Archive, there are about 50 papers. Sign language is very similar to spoken language in many ways, and so people do publish sign language papers in speech conferences sometimes. Throughout the IEEE, there are several thousand papers on sign language. Within the IEEE and computer vision publications, there are about 128 papers. And then there's a big bunch of papers in the Vision Foundation conferences like ICCV and so on. And as far as I can tell, are not searchable, but I expect that there's quite a few there. So that gives you a sense of how the community is sort of spread out. And in our own work, we've published in all of these venues. Okay, so in the rest of the talk, I'll give a little bit more background on sign language understanding data and tasks, including some data sets that we collected. And then I'll be giving some case studies from our own work, some of our recent work, and also some of our not so recent work, just to put things in context, because I assume that this audience maybe doesn't see a lot of literature on sign language. Okay, so let's get started. Data and tasks. So sign language video data can come from a variety of places. One that you probably thought of immediately is you're used to seeing sign language interpreters, for example, for spoken broadcasts. So the images I'm showing here, one is from a news broadcast, and the other is from a weather report. Um, these are examples of interpreted sign language. So they start out as some spoken language, and then they're interpreted into a sign language. There are also some sign language media that are native or non-interpreted sign language media. So they were produced originally as sign language and not translated from any other language. So there's news that's aimed at deaf audiences that's produced natively in a sign language. There are also social media websites like deafvideo.tv where people publish video blogs about a variety of topics, leave comments for each other. The comments are themselves sign language videos. So these are all not interpreted sign language. And if you've worked on translation at all, you know that translated language will often have somewhat different form than native language in the target language. So people use the term translationese to describe uh, the type of the type of syntax that's often used in interpreted language versus native language. And for sign language, there can be a very big difference between interpreted versus native sign. So one of the challenges of dealing with sign language in the real world is finding enough natively signed data. Okay. So what are some tasks? One of the most typical tasks that we deal with in sign language understanding is just isolated sign classification. So the input is a video clip of a single sign, so it's a sequence of video frames, and the output is the corresponding word or gloss. You may have seen the word gloss used in other translation work. It just refers to a label for the word, which may or may not be in an actual dictionary, because the word may not exist in any written language. There are a bunch of data sets that have been collected over the years. You'll see some results on this last one, WASL 2000, a little bit later on. A related task is sign spotting or keyword search, where the goal is I'm given a video clip of a full utterance of in some sign language and a query word, for example, steel, and the output is just yes or no, is it in this utterance? So this is very similar to the keyword spotting task for speech. Finger spelling recognition is an unusual task in that there's no written form for sign language. Sorry, not finger spelling recognition. I'll come back to that. Finger spelling recognition is not an unusual task. In finger spelling recognition, we're given a video clip that corresponds purely to finger spelling, and the output is the sequence of words that it corresponds to. And similarly to sign spotting, we can also do finger spelling detection, where the goal is to determine where finger spelling occurred in the video versus other types of sign. Um, okay, here's what I meant what I was starting to talk about before. Sign language recognition, continuous sign language recognition is a little bit of an unusual task because there's no written form for sign language. So here the input is raw sign language video and the output is a gloss sequence. So the gloss sequence consists of, in this case, words in English, but also elements that don't occur in English, like move furtively is not its own word in English, but is a sign in sign language. And pointing is a type of gesture in sign language that doesn't correspond to any English word, so we have a gloss for it, labeled point here. And just by looking at this gloss sequence, you may not be able to tell what the intended meaning was. And usually the end goal is sign language translation, to actually write down a written language sequence corresponding to the meaning of the video. So in this case, the meaning is moving furtively, pirates steal the boy Patrick. Okay. And this sort of data, gloss annotation, is fairly rare to find because it requires expert linguistic knowledge about the sign language. It's not something that people normally write down for sign language. Okay. So sign language translation is probably the most popular task for sign language. It seems to be um, the most kind of practical task for enabling signers and non-signers to communicate with each other. If we had a Google Translate for sign language, then that would immediately improve the quality of life of signers trying to interact with non-signers. And this is a big list of a bunch of sign language translation data sets collected over the years. This is in chronological order. And what I wanted to point out here, you can see that over time, the vocabulary size has increased, the amount of data in the data set increases, and the number of signers increases. Some of these data sets include both glosses and translations, mostly the smaller ones. Almost all of these are interpreted sign language, and almost all of them were recorded in a studio setting. Only these last three, OpenASL and YouTube ASL, and YouTube SL25, are natively produced sign language, natural sign language. And of these natural signing data sets, only OpenASL provides dev and test splits and glosses. So it's the only one that's really used for evaluation. The others are used more for pre-training. Okay. So if we look at just example frames from these data sets over time, we can sort of get a sense of how the field has evolved, how sign language research data has evolved. The earliest data sets were really studio settings. Signers were invited to come into a recording studio and record themselves. And then later on, people started using naturally existing sign language interpretation data from broadcasts and so on. So there are more viewpoints, more challenging backgrounds, and so on. Um, and I'll be talking later about two data sets that we collected, which are Chicago fingerspelling in the wild and OpenASL. And I just wanted to place them on the timeline here, and I'll be talking about them more later. Okay. So when we talk about sign language in the real world, there are few different dimensions of variation that we can think of. One is visual variability. So if we're recording in a recording studio versus a news studio versus just amateur webcam online, um, this goes from very controlled visual settings to very challenging visual settings. Um, the size of the vocabulary, of course, makes everything more challenging, just like it does for spoken and written language. Um, the linguistic complexity of the domain can make things more or less challenging. So isolated signs are perhaps least challenging. Scripted sentences, like in a news broadcast, are more challenging. And then spontaneous or conversational signing is the most challenging. And then there are other dimensions of variation that aren't shown here, like the number of signers, whether or not it's interpreted, and so on. So our goals in all of our work have been to deal with sign language understanding that's open domain, open vocabulary, that's robust to all of these types of visual variability, and that are independent of the signer. For now, we've only been dealing with American Sign Language. We hope to expand to other languages in the future. Um, there are some technical challenges involved in this work, like there are certain off-the-shelf tools from vision research that don't necessarily work as well for sign language or well enough for our purposes, like pose tracking and hand detectors and so on. Frequent finger spelling is a challenge because it's very, very quick and co-articulated. And the lack of gloss annotations means that for real world data, we don't have monotonically aligned annotations along with the video. So that's another challenge. And that's a very similar challenge to speech translation in the absence of any written annotation. But that's pretty rare in speech-to-speech translation because often it's very easy to get some sort of written annotation, whereas for sign language, it's very difficult. So it's more similar to speech-to-speech translation from an unwritten spoken language. That would be the better analogy. Okay, so I mentioned that pose estimation doesn't work well enough. I just want to show you what I mean. So there are some very high quality existing pose estimation models out there like MediaPipe and OpenPose. And they're off the shelf. They're quite high quality for many purposes. And another nice thing about using pose as opposed to using a full image is that it reduces any privacy concerns that signers might have in sign language interfaces. But unfortunately, these pose estimators are imperfect in places where it really matters for sign language. So I'm showing three examples here taken from this paper that studied pose estimation for sign recognition. So on the left here, you see this gesture with one hand touching the other. And the active hand, the pose is really not detected correctly at all. In the second example, there's a similar gesture. The pose is a little bit better detected, but the fact that the hands are touching is not detected at all, which is a critical part of the meaning of the sign. And then on the right-hand side, we have a sign where the index finger is touching the face. The index finger is missed, and the fact that it's touching the face is completely missed. So these pose details are really critical for sign language, and they're missed here. So with that in mind, I want to tell you some case studies from our work dating back maybe 6, 7 years through today. Um, so like I said before, we're really interested in sign language in the wild. So we started all of our data collection from online native sign language media. The examples I'm showing here are images from sign language media websites that we collected data from. And the nice thing about online ASL media is that there are large numbers of signers. It's open domain, it's natural, it has a lot of variability. Um, Oftentimes, it also comes with high quality English captions that are aligned roughly at the sentence level because signers who put out this media would like non-signers to also have access to it. And so they get interpreters to provide captions in English. There's also a lot of finger spelling in this data because it involves a lot of names and technical terms and so on. Some of the downsides of using data collection from online media. One big one is that the data has various licenses. And for the purpose of academic research, we can use, the idea of um, academic free use, but a lot of industrial research groups can't use this data. So that's a downside. But for now, it's been the only source of data that we've been able to find. Another downside is that the data is not perfectly permanent. If we get data from YouTube or from a social media site, the users may take it down at any time. And we don't want to distribute the videos directly because of licensing issues. So we only distribute URLs and annotations, which matches the practice of other recent web data collections. So that's sort of the framework for all of our data collection so far. The first um, online data collection we did was called Chicago FS Wild, or Finger Spelling in the Wild. Um, this was the first real world ASL finger spelling data set. We got the data from YouTube, from Deaf Video TV, from a few other sites. Um, and we annotated in-house by sign language linguists and linguistics students. Um, and there's a second version of it, Chicago FS Wild Plus, which is larger and also has crowdsourced annotations. There's a bunch of more information, data, and the associated papers at this link for anyone who's interested in using the data. Okay, so what are the visual challenges in this kind of data? I mentioned co-articulation before. Here are a few examples. Um, these are examples of the same signer producing different finger-spelled letters. So on the left are four figures that all look fairly similar, but correspond to four different letters. And on the right are three images that again look fairly similar but correspond to three different letters. Um, Here, on the other hand, is the same letter, six images of the same letter produced by different signers in different settings. And as you can see, there's often a lot more variation within the same letter as we look across signers and settings than there is across different letters in the same setting. Um, so this is a big visual challenge. Um, let's move on to tasks. So the first task we use this data set for is finger spelling recognition. So here we have an input video clip like this, which corresponds to a finger spelling sequence. And the output that we want is the letter sequence. Um, there are a couple of papers plus a PhD dissertation that describes our efforts on finger spelling recognition. For purposes of this talk, I'm just going to summarize it all in one slide. Um, First of all, we measure performance as letter accuracy. This is like 100 minus the letter error rate. Humans over on the right, these are human proficient ASL learners. These are not necessarily native signers. They have a performance close to 80%. And when we started this work, we started with some handcrafted, sign language specific hand detectors, and we're able to get about 40% letter accuracy. But we really didn't want to use these very high effort types of detectors. So we moved on to using the whole image, which the first thing that did was to reduce performance greatly. Um, and then we introduced an idea that we call iterative attention, which is a way of iteratively zooming in on the relevant parts of the image automatically, which improve performance a lot. Then we introduced something that we called a two-stream conformer, which deals with the multiple streams of information in the hands versus the face, and that improved performance. And then we added a bunch of crowdsourced training data from Chicago FS Wild Plus, which got us actually quite close to human performance. Letter accuracy in the high 70s. And so that's where we sort of left things with finger spelling recognition. So that task, I would say, for this data set is almost solved at the level of human performance. Even human performance is not perfect on this task. Um, and then we moved on, but I want to show you some examples before we move on. So these are a couple of videos of finger spelling. And then under each one, you can see the hypothesis from our best model and the corresponding ground truth. So one is science fiction, one is open source. Um, Now, all of that work assumes that we know which portions of the video correspond to finger spelling. If we don't, then we also need to detect the finger spelling portions. So here's an example of the entire sentence that we've looked at already a couple of times. And what we'd like to do is find just those two segments that correspond to finger spelling and transcribe them. Um, and I won't go into the details of our model for this, but I just want to show you an example of this in practice. So this is a news broadcast in American Sign Language, and our detector is detecting in the red boxes instances of finger spelling and then transcribing at the bottom each finger spelled sequence. And by now, you've maybe seen enough videos that you could also do the finger spelling detection task. Whenever the person has one hand up and is only using the one hand, that's typically finger spelling. Um, okay, but I want to move on um, from finger spelling. So the task that I'll spend most of the rest of the time on is sign language to English translation. So here,
Sorry, before
yes.
you, I think there's a question in the
Oh,
chat.
sure. Yes.
I'm curious about the latency for these models. Are they suitable for real-time use?
Yes, good question. So the timing information escapes me right now, but I think the answer is no, not quite. Um, yeah, I'm sorry that I don't remember the timing details. You might have to check the paper for that or email me afterwards, if it's not easy to find the information. Sorry. We really were not focusing on real time at all at that time. And so we would do things like, offline compute all of the features, um, and um, and not really try to do things in a streaming approach. But that's of course very important. Okay, so moving on to translation. So here the task is given an input ASL video, we want to output a corresponding English sentence. We're assuming that each sequence corresponds to a single sentence. And for this purpose, we collected OpenASL, which is, I think, the first real world non-interpreted ASL translation data set. So this was collected from online ASL videos. It was a collection of news websites shown at the bottom, as well as videos from the National Association for the Deaf, which produces YouTube videos consisting of announcements and tips and conversations. And so these are more natural. And we divided them into utterances corresponding to the captions that existed on these sites. So we restricted ourselves to sites that had corresponding captions. And then we split the data into train, development, and test. And then our dev and test sets, we had a professional captioning service manually refine the utterance started end times and the translations, and also add glosses um, so that we have a nice clean dev and test set, while the train set is a little bit noisier. Okay, so for this purpose, we built a translation model. I should start by saying this is an extremely challenging data set. So the first thing we did was get extremely poor performance with our baseline models. Um, uh, but the model that we eventually developed, and this is Bowen Shee's PhD dissertation work, part of his dissertation work, is a model that um, uses the fact that sign language can be decomposed into these multiple streams of information. In addition to the global image, we had hand-specific and mouth-specific representations. So these were separate streams, and they were fused with the cross attention um, uh, component. And we also used pre-training to learn better representations of each of these streams. And for the most part, this pre-training was supervised and really sort of built for the purpose of each of these representation streams. So the global encoder was pre-trained on isolated sign classification using the WLASL dataset, as well as using weak supervision from sign search on OpenASL. And then the hand decoder was pre-trained as a finger spelling recognizer, whereas the mouth decoder used pre-trained representations that you might be familiar with from the A.V. Hubert model, which was trained for speech, but also works well at representing images of speakers' mouths, even if they're not speaking but signing. And without going into too much detail, our best performance on this data set was a BLEU score of 7.5 and a BLERT score of 34.5. I don't know how familiar people are with these scores, but this is a very poor performance. So reasonable translation models usually get at least 30 BLEU is when they start to be usable. So on the other hand, we were quite happy that unlike with the finger spelling data set, we did not reach human performance, so there was a lot more research left to do. So this was 2022, and a lot has happened since 2022. And fast forwarding to the LLM era, um, more recent models are, of course, trying to use existing LLMs to do the task of ASL to English translation. And so I wanted to mention a couple of recent, very interesting papers that are sort of starting points or comparison points for our more recent work. Um, one of them is from NeurIPS 2023 from a group at Google. And this paper, the goal of this paper was really to introduce the YouTube ASL dataset for pre-training sign language representation models. But along the way, they also got some interesting sign language translation results. So they collected this YouTube ASL data set of about 1,000 hours of weekly label data. They did not do all the cleanup that we did for OpenASL and did not split it into train, dev, and test. So what they did was they pre-trained on YouTube ASL and they tested on another data set, which is how to sign. How to sign is an interpreted data set, but has other nice properties like very large vocabulary and variety of signers. And what they did was they took the video frames, passed them into a pose tracker, and all of their models actually used pose trackers only, despite the fact that pose trackers are imperfect. Took the landmarks from the pose tracker, passed them through a linear projection, and then fine-tuned a T5 model along with that linear projection to translate from the sign language features to English output. So that was sort of a landmark in the progress of sign language translation. And then another very exciting paper was from Meta at ACL 2024 last year. Um, so this paper again used YouTube ASL, used a very similar setup to this previous paper, but moved away from pose tracking to get better performance. And they developed an approach for self-supervised pre-training of a video encoder on YouTube ASL to improve performance on how to sign. And so what they did was they took an existing video video encoder that had been used for non-sign language called Hiera, and they continued pre-training of Hiera on sign language data from YouTube ASL, and that produced an encoder that they call Sign Hiera. So this is their first part. And then they did something very similar to the previous paper. They used the extracted features from the encoder as input to a pre-trained T5. They kept the encoder frozen. And oh gosh, I'm so sorry. My battery is running low. I'm going to grab my adapter. I'll be right back. Sorry about that. Um, so unlike this previous work that just used a pose extractor, now they were using full image frames and full video sequences. Um, so they lost some of the privacy properties of pose estimation. But what they did do was they blurred the faces in the video to improve privacy. And they got nice results on how to sign. However, um, this work required 64 A100 GPUs for 14 days, um, which is a lot, especially for academic research groups. And so this is where our recent work comes in. The first piece of work I want to tell you about is trying to um, match this performance of these recent models, but with academic scale compute.
Sorry, there's a question in the chat
Yes.
on the previous slide. So from this figure, it looks like they blurred the face of the target in the pre-training step. Isn't face an
Hmm.
important part of the pipeline?
Is what part of the pipeline? Sorry.
Isn't face an important part of the pipeline?
That's a very good point. So the face is a very important part. Um, and they argue that the blurring doesn't remove, the gross motions of the face. And they did do some ablation studies looking at the effect of the blurring. Um, and it's just a trade-off. Um, if you really insist on privacy, then you might not want to use the full resolution frames, but you might lose a little bit in performance. And so for our work, we did something a little bit different, and I'll show you in a moment. Um, so this first piece of work we call Sign Musketeers. You can maybe by the end of the next few slides, you'll know why it's called Sign Musketeers. Um, what we what we did in order to get this task to be doable on an academic budget was first we decompose the video frames into the streams that are relevant for sign language. So just like in the previous work that I described before, rather than looking at whole images, we decomposed it into detected faces, detected hands, and then we also added an overall body pose. So we do use a pose tracker, but we don't rely on it entirely. So already this is much less data than the full video. Another thing that we did was to, rather than learn video representations with a video transformer, we learned image representations, um, which again is a lot less computationally demanding. And that allowed us to use a drastically downsampled subset of YouTube ASL for pre-training. Okay. And what this what the process looks like is we pre-train an image model. We started with Dino V2 because there had been some previous work comparing various image models for sign language, and Dino V2 um, seemed to be the most promising. So we started with Dino V2, and then we fine-tuned it, or really continued self-supervised trained it on face images on the one hand, and this gave us one encoder, which we called Dino V2F, and on hand images on the other hand, and this gives us our second encoder, Dino V2H. And that's the self-supervised component, and that we did on a downsampled version of YouTube ASL. And then we turn that into a translation model by extracting features from these encoders, which we keep frozen, adding a stream for the body pose, and then learning a projection layer, learning multiple projection layers, and fine-tuning a T5. So the T5 part is quite similar to the previous work. And this gave us some interesting results. So what I'm showing here is on the x-axis, the GPU hours used, and on the y-axis, the blue score. All of the blue markers are our results, and then the yellow and red markers are from the previous best performing model. And the size of each marker corresponds to the number of data frames that were used to train the model, to pre-train the model. The rest of the pipeline is similar. It's pre-trained on YouTube and then fine-tuned on how to sign. And the main point to look at is this one, which is our model pre-trained on YouTube, fine-tuned on how to sign, and reaches almost as good performance as this prior work while using about 40 times less pre-training data and about 3% of the compute. Now, it's possible that the prior work, didn't try very hard to reduce compute. We don't know. But the changes that we introduced were explicitly aimed to enable using less compute. Okay. So unless there are questions about Sign Musketeers, I'll go on. So our most recent work is what we call Sign Hubert or Schubert, which is a contextual frame level representation model. And so the idea is there's been all of this work on sign language that's been very task specific. Even though there's been pre-training involved, it's been aimed at a target task, like say translation. And we'd really like to move into the foundation model era. We'd like a foundation model for arbitrary sign language tasks. And that's what Schubert is for American Sign Language only so far, but it's extensible to other languages. And so the key ideas in Schubert are first, we're going to keep using the intuition of decomposing sign language into these multiple streams of hands, face, and body. We take inspiration from Bert and Hubert for text and for speech in terms of designing the self-supervised training task and objective, because sign language is a language, and so we expect that those sorts of pre-training tasks should be useful for sign language as well. And the starting point, the contrast with previous work is that the starting point in most of the previous work on pre-training for sign language was video action representation models. And so they would take a video model like Hyra, for example, and then fine-tune that on sign language. Whereas our starting point is representation models of individual images, which is more efficient, as well as an objective that's language oriented rather than video oriented. There is one other previous approach that we're aware of that is based on BERT, for sign language, but that one is limited to hand representation. So it's not modeling all of sign language with this pre-trained model, and has not been, as far as we know, evaluated on natural signing. And why do we focus on ASL? Well, ASL has more data available, and also, most importantly for us, more natural signing data rather than interpreted data. Okay. So that's sort of the philosophy behind Schubert. So let me tell you in a little bit more detail how it works. So the pre-training stage starts out with the video sequence. We use MediaPipe, the pose estimation model, to extract regions of interest for the hands and the face, as well as track the gross motions of the upper body. So that skeleton that you see in the background there is that. Then we start off with Dino V2. This gives us 4 streams of features that are color coded according to the colors in this image. So one stream for the global pose, one stream for the left hand, one stream for the right hand, and one stream for the face. And then we follow an approach that's similar or inspired by Hubert. We do a k-means clustering of each of these streams. So now we have a set of face clusters, right-hand clusters, left-hand clusters, and body pose clusters. And these cluster IDs serve as the targets for the self-supervised pre-training task. So what is the self-supervised pre-training task? First, we mask out a random subset of the cells in this matrix of features over time. And the task is a masked prediction task. So we pass the masked features to a transformer encoder. This produces feature vectors that are now not divided by stream. All of the streams are now mixed together into a vector representation. And we then add a linear layer and a softmax to classify each of the face, right hand, left hand, and body pose clusters, given the representation that comes out of the transformer. And then just like in Hubert and Bert, we have a classification loss for each of the 4 streams. And we're, like Bert and Hubert, we're predicting the clusters only for the masked tokens. And then once we're done, that's it. Our transformer encoder is our Schubert pre-trained representation model. And then we use this model, we can use this model for arbitrary downstream tasks. We focus on 2 types of tasks, sign language translation and sign language recognition. We also have fingerspelling recognition results, but I won't show them here. So for sign language translation, we follow a similar procedure to the recent work where we pass the video through Schubert. We fine-tune a language model, a T5 language model, and that produces the written text output. For sign language recognition, we pass the Schubert model through just a linear prediction head to produce a class label. And the first set of results I want to show you is just comparing the Sign Musketeers results with pre-training with Schubert. So Sign Musketeers is just about the same as Schubert, but without the Schubert pre-training. It's using the same streams of information. So if we just take Schubert and if we just take Sign Musketeers and just train it on how to sign, so these numbers are much worse than the previous numbers that I showed because this is just using how to sign. We get a blue score of about 2 point something. If we take Schubert's last layer and use it for translation, we get about twice that blue performance. And then if we take the layers of Schubert and we use a weighted sum, which is typical in a lot of speech tasks, we get an even better performance. So this is what we ended up doing. And then we scale this up to to pre-train on more data and fine-tune on how to sign. And finally, I want to show you the results on a bunch of different metrics in comparison with the previous state of the art. So this is a radar plot. So each of the spokes here corresponds to one metric. Some of these data sets and tasks have multiple metrics, so we include them as separate results. Um, so that includes translation for how to sign, measured in terms of BLERT and blue. Translation on OpenASL measured in terms of blue, on FLIR's ASL, which is yet another translation evaluation set in terms of blue and in terms of BLERT. And then several sign language, isolated sign classification metrics on different sign language classification data sets. And then the orange line corresponds to the previous state of the art, which is typically task-specific models trained specifically for each of these tasks and each of these data sets. And then the blue is what we get by fine-tuning Schubert on these data sets in the way that I showed on the previous slide. So for almost all of these metrics, we're outperforming the previous state of the art while having a model that is applicable to a variety of different tasks. Okay. So just a few final thoughts. We've learned a bit about sign language understanding in the real world. We've learned that online caption video is a nice source of data. We've learned that pose estimation is not perfect, but it's often useful as a starting point and to locate regions of interest. And just like other low resource tasks, pre-training is very important. And sign language research benefits from knowledge about sign language. So knowing that sign language decomposes into these different streams of information, knowing its relationship with spoken and written language have all been helpful in this research. How are we doing on specific tasks? Finger spelling recognition is going really well. The best models we have match at least a proficient student of ASL. Real world sign language translation, we're making progress, but still not nearly as well, not going nearly as well as spoken or written language translation. And foundation models for sign language are just getting started. So I hope that we are now moving into the foundation model era for sign language, and I hope that we'll see a lot more of these kinds of models. There are a lot of remaining challenges, lots of additional pre-training ideas to try. Of course, more sign languages and more tasks. I just want to mention all of the collaborators that have been involved in this work over the years. So the senior members of this collaboration are Diane Brentari, a sign language linguist at the University of Chicago, Greg Shachnerovich, who's a computer vision and machine learning expert at TTI, and myself. Much of the older work that I showed you was led by my former student, Bowen Shi, who's now at Meta, and was one of the authors on the Meta paper that I cited. And our more recent work is led by Chester Gwewu, who's has been a visiting student at TTI and is a soon-to-be PhD student at TTI. And all of these collaborators have all contributed in one way or another to all of this work. And it really is very interdisciplinary work, so we really rely on having language, vision, and linguistics experts always involved. Thanks. I'll stop there. I'll leave you with some references to all of the papers that I mentioned from our sign language collaboration, if you'd like to follow up. And I'll be happy to take more questions if there are any.
Thank you, Karen, for the presentation. So if anyone has any questions, just write them in the chat, or you can raise your hand and ask them directly. Yeah, Pune.
Yeah, so thanks a lot for the interesting talk. The subject is like very unique and niche. I really like that. So one question that I have regarding the pre-training part is you mentioned that you are using like language focus objective, but I still didn't understand what is the language focus objective in the pre-training part.
So that's here, right?
Yep, exactly.
So it's inspired by models that have been successful for language. Let's put it that way.
I
So
see, I
the
see.
idea of learning contextual representations of frames that are learned by filling in masked segments of the
Huh?
signal, that has been successful for both written language and signed language and
I
spoken language.
I see, I see.
Yeah.
And when you calculate the clustering part, how the clustering is done? Is it like Hubert that it is improved when during the training, like you're getting the first layer improve or refine the clustering, or it is always the same?
So in principle, yes, we should do that, but we have not yet.
I see,
So at this point, we've just clustered once.
I see.
Um, and one thing to maybe say is that in Hubert, the initial clusters are very, very raw, right? Because they're just clustered MEL features.
True.
Here, we've done a little bit of pre-training of the Dino V2 um, representations for hands, face, and so on ahead of time. And so the clusters, maybe I should have shown them, but the paper has examples of the clusters. They look pretty convincing.
I
So
see.
I do expect that we could do better.
Mm.
But they're not terrible.
I see, I see. And
Yeah.
the loss is contrastive loss or the classification loss for this
Classification.
part? Classification. Okay, and maybe I have one general question. Is there any work like something like text to sign language or sign language to a speech? Is it any end-to-end model that is already in the literature or something?
So text to sign language is a big area um, that we have not worked on, but yes, lots of work exists on it. So generation of signing avatars
Mhm.
that serve as interpreters from spoken or written language to sign language. There is lots of work on that. What was the other one? Oh, from sign to speech.
Yeah,
Um, so I don't know that I've seen that explicitly. My guess is that at the moment, a good way of doing that would be to do sign to text and then TTS. But of course, that would lose some information. So sign language, just like speech, has prosody, has emotion, unlike
mhm.
text. So all of that would be lost, and I think that it would be a very interesting thing to eventually look at end-to-end sign language to speech that retains all of those pieces of information, just like in speech-to-speech translation, where if we don't go through text, we have a better chance of retaining that kind of information.
I see, I see. Interesting. Thank you.
Yeah, sure.
Okay, if there's any other questions from the audience, yeah, Trong Tan, you could just unmute yourself and ask your question
Yeah.
directly.
Hi, Karen.
Hi.
I don't, yeah, so I don't think I can turn on video, but yeah, I was just gonna ask, what would be the equivalent of prosody in sign language? Um, is it more related to the hand gestures or facial um expressions play a role in that?
So I'm no sign language linguist, but my understanding is that it's all of the above. So things like how fast is the motion, how big is the motion. Um, Sometimes that has semantic content, but sometimes it's just expressing things that prosody would express in speech.
Right, yeah. And so related to that, um, when do you think that is still so you said that it's an important signal for the equivalent of TTS, but once the direction is going through all these foundation models, um, do you think it's still a meaningful way to kind of tease apart this part is uh, the contribution of prosody versus we're just looking at something that has universal representation power.
So I think that that's a good point that, just like with spoken language foundation models, it might be hard to tease apart where the different sources of information are once you've learned this big representation. Um, so of course there's been work, looking at where in the models the information is, including from my group and other groups. But it's kind of a post hoc thing. Where we have a pre-trained model and we say, okay, now where's the prosody? Where are the words and so on. Um, and I think the same sorts of analyses could be done for these sign language foundation models. Um, and in principle, if we really care about keeping these streams of information separate, and if we really care about keeping them interpretable, then we could build that into the pre-training loss. But that's, yeah, I, I don't have great ideas for that, but that that would be a good thing to do down the line.
Very interesting. Yeah, thank you.
Thanks.
Yeah, there's another question in the chat. Someone asked, what are some notable limitations common across all current models of some language that you are aware of? Like, for example, requiring certain lighting, clothing, being affected by background, overfitting to certain demographics, common in datasets, etc.
Right. So in many of the earlier data sets, and also many of the currently popular data sets, there are really constrained conditions like studio recordings or small numbers of signers or constrained domains, so small vocabularies. We've really tried to work only on very natural data sets with lots of variation. And so um, in order to build models that are more robust to those sorts of things. One thing that there's been almost no work on, um, that I think is a limitation of most sign language work, almost all sign language work right now, is long form video. So a lot of times, by dealing with a single utterance at a time, we're missing references to earlier utterances. Um, and this is an issue with any language, of course, when you do short form versus long form, you lose some of the context information. But for sign language specifically, references to earlier contexts are particularly interesting. Um, so in sign language, there's usually kind of a spatial arrangement of entities that you're referring to. So like at the beginning of a conversation, I might sort of set the stage by placing one person I'm talking about here in space, another person here in space, and then the pointing motions of sign language would point to those parts, to those points in space to refer to those entities in future utterances. Now, if I just see one utterance in the future, I have no idea what it means that I'm pointing to one spot or another. I don't know if that's a him or a her or a they because I don't know, or an it because I don't know what I've placed there. So that's kind of a specific thing to sign language that really hasn't been addressed yet. There's been maybe one or two papers kind of pointing this out and starting to deal with it.
Okay, thanks. I think that is all the questions. If maybe just final additional questions. Okay, perfect. Thanks a lot for accepting our invitation and for this interesting talk.
Thank you for having me.
Sure. Next week we have Tituan Parcelet from Samsung AI Center at Cambridge, and he's going to talk about unsupervised on-device adaptation of a speech recognizer and the pitfall of speech language models. Thank you everyone for joining, and hope to see you next week.